This problem says, the figure shows a claw hammer as it pulls a nail out of a horizontal board. If a force of magnitude 169 newtons is exerted horizontally as shown, find the force exerted by the hammer claws on the nail. Assume that the force the hammer exerts on the nail is parallel to the nail. Answer in newtons. Okay, I think this one looks more difficult than what it actually is. The first thing I'm going to do is write down what I know. That is my given. This distance here, the separation, I'm going to call length L. Now this angle, I'm going to call alpha. The reason why I'm not going to call it theta is I know I'm going to have to use torque, and I want to reserve theta for the angle that goes with the torque equation. Therefore, you can pick whatever Greek letter or whatever letter symbol you want. I'm just going to pick alpha. This distance, you can think of the height of the hammer, so I'm just going to call it h. And I want to know the force of the nail, so I'm going to call that F lowercase n for nail. Next, what I'm going to do is I'm going to trace two lines that will represent the hammer. So it starts at the point of contact and goes up to the force H. That is so I can better visualize my torque. I'm going to do the same thing here. Now for visual purposes, I'm going to make this bigger, enlarge it, and then just adjust a little bit so I can use my grid as a resource. All right, now let's add the forces. We know this is force F. I'm not going to be worried about the magnitudes. And I know because the hammer is trying to get the nail in this direction, I know the reactive force by the nail is like this. There you go. Now, this distance here is this distance, the one we called L. So that's good. Let's trace that because I think you'll know what shape we are building. And we do have a right triangle. Here's my 90-degree angle. And this is alpha. Just so I don't forget, that's my length L. Okay. Now, we got to apply torque because the hammer is going to make a motion in a partial circle. And if the hammer or if the nail, for some reason, someone would pull the nail in this direction, the hammer would also take that motion in a circle, that rotation. So we have torque. Two torques, actually. We're going to assume this is in rotational equilibrium. That is, both torques are going to be balanced. Now let's just find the formula, the equation that represents each torque. This torque I'm going to call torque by the nail. And then the force is this, obviously, the force of the nail. The angle theta is 90 degrees, so I don't need to use sine theta. I need to know this distance. How am I going to know this distance? That's simple because this is L, and if you look at the triangle, this happens to be the hypotenuse. So this length over here, being that that's the adjacent side to alpha, is simply L cosine alpha. So my formula, my torque equation, which is L cosine alpha. All right. Up here, this one's very simple. Just one force. Again, there is a 90-degree angle. So I'm going to call this one just torque. It's just force times the distance. This distance is the distance h, the height of the hammer. And then sine of 90 is 1. All right. So there we have it. What do we do with that? We have to sum the torques. They're working against each other. And because this isn't rotational equilibrium is equal to 0. All we got to do is solve for force of the nail. Very simple. They're equal and opposite, these two torques. So then I just got to divide by L cosine theta. I'm sorry, L cosine alpha. My mistake. Don't forget to convert your centimeters into meters. And there we have it. Our answer, the force of the nail, is about 1,500 newtons. That's it. Stay tuned for part 2. Part 2. Find the force exerted by the surface on the point of contact with the hammerhead. Assume that the force the hammer exerts on the nail is parallel to the nail. Okay. What I'm going to do is take this sketch again without the torques. I'm not going to use torque for this one. Okay, now let's look at the point of contact. What's happening? Well, the thing we should know, there's a surface. I think they call it a board. Yeah, board, horizontal board. So we know there's a normal force. However, it's not the weight of the hammer that's creating the motion, but it's this force. Now, think of what would happen if the hammer would slip. It would just go that way. So then we know that there's a horizontal force pointing in this direction, as well as the normal force on this direction. So we'll add those two to our drawing. I'm not going to be very careful with the magnitudes. I just want the forces to be shown. This is the normal force. And we have that horizontal force. Let's call it lowercase f, C for contact. The reason why I'm calling it lowercase f is because I know I'm going to have to combine these two vectors, these two forces, to find the resultant force. And that one I'm going to call force contact, because I have these two working together. Now let's see what these are. To know, I'm going to sum the forces. Let's start with the x direction. I have force F. In this case, FC lowercase is along the same direction as F. So plus. However, this force here, force of the nail, as you can see, it's not within the same plane. Is more this plane. However, since we're using these two, I need to find the components of force F nail. So that's simple to do. I'm going to make this bigger just for visualization purposes. And I know it has components like this. So down and to the right. And we know that this is alpha. So then, this component is adjacent, so that would be force nail cosine alpha, and this would be force nail sine alpha. All right, we can continue summing the forces. Because force sine alpha is against these two pointing to the left, get a minus sign. Again, this is in equilibrium. This would be 0. We got to solve for this force. With a little bit of algebra, not too complicated, we'll get this expression. Now, let's sum the forces along the y direction. We have normal force minus this one. Only two forces, that means they're equal and opposite. So now to find the combination of the two vector forces, force vectors, what we gotta do is apply that formula that looks like the Pythagorean theorem. So it'll be this one here. We know what these are. I saw my mistake. It should be cosine alpha. And there we have it. 1,386.77 newtons. That's the force at the point of contact. Be careful with your computation, that is when you use the calculator. It is very easy to make mistakes. I made a mistake, not just with the cosine. I put the square in the wrong spot, but then I saw the force that didn't make sense. So I just went back, reviewed, revised my operation, and placed the square correctly. That's it.